Okay, welcome back. The aim today is to discuss Wick's theorem, and we are going to step us through it with some simple examples, and we are going to show it for 2 operators, 3 operators, and 4 operators, and then we are going to show the theorem, which is normally done by induction. And then the theorem is pretty easy to prove. And it's going to save a lot of time when we are going to evaluate expectation values. So the thing I wanted to bring up first, before we start with Wick's theorem, is actually to remind ourselves about that exercise or that example which we looked at yesterday. And I'm going to bring it up again because this is a clear example of something which begs for simplifications. And that is what Wick's theorem is going to give us. So let me bring up the example which we had yesterday. And let's just go through the different steps because this is also linked with the exercises which we have today. So the example which we looked at yesterday and where we, in a very, very brute force way, we try to calculate the expectation value of a one-body operator. And one thing which we haven't showed yet is the expression for the one-body and two-body operators in second quantization. This is something which I will defer to next week. It's a technicality, but it's something which I will run through via the slides because it's not one of the most exciting things to do on a blackboard or whiteboard. But now we are just going to use the operator H0, which we now are simply going to state is given in terms of this summation over states, alpha, beta. And then there is what we have loosely called a matrix element. And normally we would assume that this is an integral, as we have defined in the beginning of the semester. And we will normally assume that this basis which we have chosen, which we normally call a computational basis, is an eigenbasis of this operator H0. That's a pretty common approximation in many body theory. But keep in mind, and this is something which we also mentioned in the beginning of the semester, is that the approximations which we are developing now, they are based on us assuming that a single particle basis is a reasonable starting point for approximating a many-body basis. And this obviously breaks down if you have strongly interacting systems, like you would have in Bose-Einstein condensates when you have a liquid helium or liquid helium-3. These are examples of extremely strongly interacting many-body systems, so-called quantum liquids, which undergo phase transitions at low temperatures, the superfluid state. And these are systems which are strongly interacting and where this picture, which we are building up now, actually breaks down. This kind of picture is useful if you are doing atomic physics, molecular physics, most examples in condensed matter physics, solid state physics, if you're dealing with nanotechnology, semiconductor physics, even nuclear physics, where still a single particle basis is meaningful. So what we did then was to introduce the creation and annihilation operators. So you can rewrite this in what we call the number representation or Fock space, or sloppily second quantization. And what we did yesterday was to set up the expectation value of a two-body state in terms of this operator. And we went through in a very, how to say, not very smart way by doing all the possible contractions. So let me quickly remind you of that, because then you see immediately how slow this process can be. And then you may actually ask yourself, what's the point of doing second quantization when you get something which you can do equally well with the standard write out of a state function like a Slater determinant and calculate the expectation values, as we did last week. So what we ended up with then was something like a sum which runs like alpha and beta. We have now this specific matrix element. And this is a transition probability or expectation value if we have the same states. So I will sloppily call these for matrix elements. Because at the end, when you are setting up your calculation of machinery, you will tabulate these integrals in terms of vectors and matrices. And then people often label these simply as matrix elements. So that's a kind of word which I will be using for these actually integrals. And then what we have to do then is to calculate these operations here. So we have the transposed state, alpha 2, and then we have the operator alpha, A alpha 2 and A alpha 1. And then we have A dagger alpha, A beta, and then we have A alpha 1 dagger and A alpha 2 dagger. Now, normally when you're going to run these operations, we skip the two vacuum states, which we have on the Brown-Niket side. And we would simply just set this in terms of A alpha 2, A alpha 1, and then we are going to rewrite this in terms of different contractions. And the whole idea is that we want to bring these expressions so that we have an annihilation operator to the right, because the annihilation operator acting on the vacuum state, which you have here, is just going to give us 0 by definition. So the whole thing now is to use anti-commutation rules so that we can shift the operators. And this is the basis of Wick's theorem, where we are going to have a series of specific terms, which we call normal order terms, which then we can automatically just set to 0. So let's repeat this contraction just to, how to say, abuse on your patients and show you actually that this is not the best way of doing things. And this motivates both the introduction of Wick's theorem. Wick was actually an Italian Jew, Giancarlo Wick, from the University of Pisa. And he made significant contributions to particle physics in the beginning of particle physics in the 50s and 60s in the last century. So that was a small digression. So let's take a look now at this operator. So what we did, we started to rewrite it, and we have an A alpha 2 here, A alpha 1, and then we use the anti-commutation rules, and we interchange this alpha beta. So I just did one parenthesis too early. So alpha 1, A alpha dagger, and then we interchange this A beta with A alpha 1. So we get a Kronecker delta of beta of alpha 1. And then we have a minus A alpha 1 dagger, A beta. And then this is multiplied with A alpha 2 dagger. So that's the first manipulation, where we now are trying to bring one of these annihilation operators to the right. So that will give us immediately, when we calculate this expectation value, we are going to get something which is equal to 0. Okay, so let me switch then. So just keep this expression in mind. And if we just look at the first one, so the first term is going to give us the following. That will then be equal to A alpha 2, and then I have an A alpha 1, and then I have an A alpha dagger, and then I have an A alpha 2, and this is a delta alpha 1 of beta. So that means, as an aside, when we are looking at the double sum of alpha and beta, so we have this double sum alpha and beta, and there we have this integral. So we have an alpha and H0 and beta. So we are going to take away one of the elements in the sum. So we will just get the sum of alpha with this Kronecker delta, which you see here. So that will simply give us a term which goes like alpha H0, and then I have alpha 1 here. And then if we look at this first term, what we can do next then, when we manipulate this further, you see now that one of the things we would do is simply to switch alpha 1 with alpha. So if we keep working on that term, we will get an A alpha 2, and then I have a delta alpha 1, and then I get a minus, and then I have an A alpha 1, and then multiplied with an A alpha here, dagger, and then multiplied with an A alpha 2 here. So if you now look at the term which we have, this Kronecker delta, so this Kronecker delta is now going to take away the sum here so that we actually have an alpha 1 of H0 and alpha 1. Then we are left with, if we take the first part, the one which links with this one, so we would then have an A alpha 2 dagger, and then we have the Kronecker delta of alpha and alpha 1. And this one, when we now are calculating it, this is the same as us, because the Kronecker delta doesn't enter this expectation value. So this would be the transition from a state which has alpha 2 to a state with alpha 2. So, and this is again equal to delta alpha 2 of alpha 2 minus A alpha 2 dagger A alpha 2. The second term gives 0. So this simply gives us delta alpha 2, which is an obvious statement because alpha 2 has to be equal to alpha 2. So that's a pretty obvious statement. Now, if we then look at the second term, which we have here, we would then have a minus, and then we have an A alpha 2. So the second term here of this expression. Then we have a minus, and then we have an A alpha, and then we have an alpha 1 of an A alpha 2 dagger. So if we look at, no, not, it's an alpha 1, sorry, that one, A alpha 1, like that. Now here we would again use the anti-commutation rules. So we can rewrite this one as a minus A alpha 2, A alpha here. And then I have the following expression. So it should be an alpha dagger here. And then I will get a delta alpha 1, alpha 2, minus an A alpha 2 dagger, A alpha 1. And now you see that the second term, which we have in this second term, this piece here we have a operator which acts as an annihilation operator on the vacuum state. So we have moved the annihilation operator to the right. So that gives us automatically 0. So this is 0. Then this has also to be equal to 0, simply because alpha 1 is different from alpha 2. And these are fermions, so we cannot have more than one particle in one single particle slot. So this second term is 0. And that means that for the first term from the previous equation, what we are left with then is this contribution here. So that's something which, if now alpha 1 is an eigenbasis of the H0, this translates, if it is, it translates into this eigenvalue. And this is one of the terms which we had last time. So that was the first term. And then we can do the same exercise with the second term which we have here, which is actually this term here, multiplied with the rest. And we do the same exercises again and again. So let me just do it. It's not for the fun of it, but simply just to show that this is not the way we would go, particularly if you now have a 10-particle state and you're acting on with a one-body operator. This is a nightmare. If you have a two-body operator, if you're doing nuclear physics like me, where you have three-body operators, etc., this is a nightmare if you want to use this recipe. Here we go. So let's keep on staying not too smart or ignorant about Wick's theorem. It's perhaps a better way of saying it. So we can now, if we take the second term, we then have something which, and then I have to fetch it back again. So we can rewrite the second term from that expression. And the second term runs like a minus, and then I have my A alpha 2 here. I have my A alpha 1. I have my A alpha, and I have my A alpha 1 dagger. And now I'm interchanging in the last term which we have here, where we now had this term which we rewrote here, this term here. So it's essentially this piece multiplied with that piece, which I'm going to manipulate now. So when I do that, I can rewrite one of them in terms of the Kronecker delta, so I get a delta beta alpha 2 here, minus an A alpha 2 dagger, and then I have an A B. And we know that the last term has to be 0, because now we actually have an annihilation operator to the right. So this term here, that gives us just 0. So then we are left with a term which runs like minus alpha, A alpha 2, A alpha 1, A alpha dagger, A alpha 1, and then I have a delta beta alpha 2. So that means that now we are fetching a matrix element, which is alpha. So we're getting rid of the one of the sums, and then we have H0 and alpha 2 here, but we still have a sum over alpha. So if we look at this element, what we have now is minus A alpha 2, A alpha 1, A alpha, and alpha 2 is equal to beta. So that means that we can now repeat the same exercise by changing A alpha 1 with A alpha. So this is simply going to be equal to minus A alpha 2. And then I have a Kronecker delta, which says that alpha is equal to alpha 1 minus, and then I'm going to have an A alpha dagger, and then an A alpha 1 acting on this A alpha 1 here, like this. So if you now look at what we have here, the first term here, which has an alpha with alpha 1, it does not need to be 0. So this would pick a matrix element, the first term here, which looks like alpha 1 and H0 alpha 2. So that integral doesn't need to be 0. But if we assume now that these states are eigenbasis states for H0, then it would be 0, if we made that assumption. But it doesn't need to be like that. So let's just leave it as a non-zero term, a potential non-zero. But if we have chosen this as an eigenbasis, the alphas, then clearly this would be equal to 0. But what we have then, if we look at the first term, we have a minus and then an A alpha 2 and an A alpha 1 dagger. And this term has to be 0 because alpha 1 and alpha 2 are different. And you see that immediately, because then you would have a Kronecker delta, delta alpha 1, delta alpha 2, which is 0, since they're different states. And then I would have minus A alpha 1 dagger, A alpha 2, and this acts on a vacuum state, where the second term gives 0, and this term gives 0. So what is happening now is, even if we haven't made an assumption about an orthogonal basis, no, not an orthogonal basis, but an eigenbasis of H0, these terms are actually ruled out. So the only thing which can contribute now is the second term which we have here. So that means the term which you see here, the second term of the second term. And if we look close at that one, we are going to have an operator here, this one, which we then can manipulate immediately by the Kronecker deltas. And that's simply going to give us delta, the Kronecker delta of alpha 1, which is an obvious statement. And then we are left with alpha 2 with A alpha here. And that is going to force alpha to be equal to alpha 2. And then when we go back again, we see now that this term here, this one, this with that one, and here is simply going to enforce alpha to be equal to alpha 2. And so that gives this term here, gives us simply alpha 2 of H0 alpha 2. And this would be epsilon alpha 2 here. So that means if we collect everything together, what we end up with then is that this expectation value, alpha 1, alpha 2, of this one-body Hamiltonian of alpha 1, alpha 2, is simply equal to epsilon alpha 1 plus epsilon alpha 2. And this is what we had in the very beginning of the semester. When we wrote everything out with all the spatial degrees of freedom, we set up a two-particle Slater determinant, and we run through the calculations. So as you see, I hope this example convinces you that if I were to suggest doing exercises like this, you wouldn't like it. So what Wick come up with was an extremely elegant theorem. And so let's go through Wick's theorem first by some examples with the 2, 3, and 4 creation and annihilation operators. And then we're going to use that one to move on to a more general formulation of the theorem. So what we defined yesterday, if we now look at this expectation value here, A alpha, A beta, 0. This is the same as delta alpha beta, as we said yesterday, minus a term which we know is equal to 0. And we have an A beta, A alpha of 0. What we did was to rewrite this in a specific way. So we rewrote this in terms of a delta alpha beta plus something which we call the normal ordering. So N stands for normal ordering, and it means that we can take an operator, a chain of operators like here, and then we order it so that we have all the creation operators to the left and the annihilation operators to the right. And this normal order product, which is the same as the quantity which you see here, this quantity is automatically 0. So when you see something like a normal order product of operators, that's always going to give us 0. So you can see that in a case with 2 operators, which we defined yesterday. And this will be the first step in Wick's theorem. The first term is normally called a contraction. So you will often see this one. And now we are relating these to the what we will call the true many-body vacuum. That means that we have no single particle slots which are occupied by particles. So the operators create a particle in a given single particle slot. So we would typically write this like this, and this is normally called a contraction. So we are contracting the operators so that alpha has to be equal to beta. And then we have the normal order product of N, A alpha, of A beta. Now, this last term is actually, in this specific case, is minus of 0 of A beta of A alpha of 0. So I'm going to put in the definition of the normal ordered operator, and that's going to be a product of the chains of operators, which are all normal ordered. And in order to achieve that normal ordering, we need to interchange operators, and the number of interchanges is going to give us a phase. And what you see here, we have interchanged 2 operators, and that gives us a minus sign. So the general formulation then of this normal order product is as follows. So the normal order product this is now given so that if I have a chain of operators, this N, and then these are X, Y, Z's up to W, these can contain products of many operators. This could be a chain product of all operators, X, Y, Z, W, and this is going to be given by a minus sign P, where P is the number of interchanges we need to do in order to bring it into a normal order form. So that means that we would have a product of creation operators multiplied with a product of annihilation operators. Annihilation. And just as a simple example, suppose somebody gives you, so this minus this P is the number of interchanges of operators. So suppose we have an example which runs like this, A alpha 1, and then I have an alpha 2 here, and then I have an A alpha 3, and I have an A alpha 4. So this is just a simple example, A alpha 5, and then an A alpha 6 here. Now, if I want to change this into a normal ordered form, so I'm going to have a minus, and let's do the counting first. So I would have an A alpha 1 dagger. I have an A alpha 4. So to change alpha 4 past alpha 3 and alpha 2, we need 2 interchanges. So that's 2. And then I have A alpha 6 here. And then comes A alpha 2, A alpha 3, and then A alpha 5. So to change the next one, since I now changed alpha 4, so I've changed alpha 4 and placed that together with alpha 1. You see now that for alpha 6, I would need 1, 2, and 3. So that gives me minus 5. So this is going to be minus 5 here. And that will be the set the chain of operators which we're going to evaluate. And now the thing is that if I now calculate any kind of transition probability or expectation value with this change of operators, this is going to automatically be 0. If I act on a true vacuum, later we are going to redefine the vacuum state. And that's simply because we want to reduce the number of degrees of freedom. And that is something which is going to be called the particle hole formalism, where we then rewrite the vacuum state and redefine the type of annihilations and creations with respect to a specific vacuum, which could be the Fermi level of a fermionic system. So in general, what we have then, when we now calculate a quantity like this of n, and then we have x, y, z, as a chain of operators, this is automatically 0, since we always have, since we have something like an A alpha to the right, and this we know is equal to 0. And similarly, if I have a creation operator acting to the left, this is also automatically 0. Okay, any questions so far? Okay. So let's look at more examples, because we are going now to build up Wick's theorem for 2, 3, and 4 operators. And based on that one, we can generalize Wick's theorem to more complicated type of operators. So if we now take 3 operators, and the thing which is interesting with 3 operators is that as long as you have an odd number of operators, it means that you will have a different number of creation and annihilation operators. This is a term we never consider because it's automatically 0. And you will see that immediately, because when you perform the contractions, you will always be left with one operator. And being left with one operator, whether it's a creation or annihilation operator acting on vacuum states, is always going to give us 0. But let's rewrite this in this not too advanced way, which we started with. So we can rewrite this one using the anti-commutation rules as a delta 2 free minus an A free dagger and then an A2, like that. And then if we now look at it, we can rewrite this as an A1 delta 2 free. And then we have minus, and now we are going to reuse the anti-commutation rules. So we have the annihilation operators to the left, to the right, sorry. And then we will have a delta 1 free minus an A free dagger A1, and this acts on A2 here. And when we collect everything, we have an A1 delta 2 free, and we have a minus delta 1 free of A2, and then we have a plus an A free dagger of A1, A2. Now, if you now look at what we have, this is a very interesting result, because you can write this in a very special way. So you can write the first term as a normal order product of the operators A1, A2, and A3 dagger, but where you now have one contraction here. So the Kronecker delta means that 2 of these operators team up in order to perform this operation, which leads to a contraction, which is essentially a vacuum to vacuum transition. Okay, so that's a way to rewrite the first term where we now use this definition of contractions and normal order product. So we're just left with one operator here, and that's A1, so that's already normal ordered. Then if you look at the next term, we are going to have plus n, and now we are going to have an A1, A2, and A3. Now what happens now is that I have to interchange A1 and A2. So this interchange gives rise to a minus sign. Because if I want to calculate a vacuum-to-vacuum expectation value for A1, A2, A3 dagger, then I need to bring A1 close to A3. And then I have to interchange A1 and A2. And that gives me a minus sign, which is the minus sign which we have here. And then I have plus the last term, which is just A3, A1, A2 dagger. And here we have no contractions. Now, pay attention to one thing here. There are, in this specific case, when we use this rule, there are no A1, A2 contractions. They are automatically zero. In the same way, we would have, let's say, an alpha and beta with a creation. This is also automatically zero. Okay? So when I'm going to say now the sum of all contraction, it means that you could assume that you also have these, which now automatically give us zero. In our case, then, when we perform these operations here, those specific contractions are not present because alpha A1 and A2 are annihilation operators. Any questions so far? So I can actually rewrite that one like this. And so the next thing we're going to do now is to take the next example, which is the case with the 4 operators. So I'm just setting up a total random chain of operators. Now I have ordered in this specific way of 0. And if I go through this in a normal way, I would rewrite this as an A1, A2 here, and then I have a delta. Sorry, not that one. I was looking up. Let me just rewrite it A1, and then I would have a delta 2, 3. So that's a contraction minus A3 dagger A2 here, and then I have A4 dagger. So I'm just using the anti-commutation rules. So this will be the same as A1, A4 dagger acting on with a Kronecker delta, delta 2, 3. And then I have minus A1, A3 dagger, A2, A4 dagger. And then I can keep manipulating these terms. So this becomes equal, and this is something which I keep as it is. And then I have a minus, and then I have a delta 1, 3 minus A3 plus A1, and then I have an A2, and then an A4 dagger, like this. And then we can continue. So what I would get then, if I write things out, I have a A1, A4 dagger, delta 2, 3, minus a delta 1, 3, and then A2, A4, plus this A3 dagger, A1, A2, and A4. And now I'm going to rewrite this further in terms of a set of new applications of this anti-commutation rules. So I'm going to get an expression for the final ones so that when I put everything together, I'm going to get something which looks like this. So I will have a delta 2, 3, 2, 3. I'm going to have a delta 1, 4 minus an A. This is the first term. And you see now that the last term is going to give us automatically 0 because now I have the annihilation operator to the right. I get a minus delta 1, 3 and delta 2, 4 minus an A4 dagger, A2. The last one is also going to give us something which is 0. Plus I have an A3, A1, and I have a delta 2, 4 minus an A4 dagger A2. And this is something I will manipulate further, and it's going to look like as follows. I'm going to have a delta 2, 3, delta 1, 4, minus delta 2, 3, A4, A1, minus delta 1, 3, delta 2, 4, plus a delta 1, 3, A4 dagger, A2, plus, this is very exciting as you can see, but you will see a pattern here now, which we are going to use to formulate the general theorem. And then you have an A3, so just bear with me, an A3 dagger, A2, delta 4, 1, plus the final term, which is A3 dagger, A4 dagger, A1, A2. So what the Giancarlo Wick saw is that you can rewrite this in terms of contractions and normal order products. So if you look at the first term, which we have, so the first term, which is this one, so these are just two contractions. So that's the normal order product of A1, A2, A3, A4. So it's A2 with A3. We have a delta 2, 3, and then A1 with A4. So these are the two contractions which we're making for that first term. And we can always write this as a normal ordering, but we are performing the contractions inside the operators. And that's give rise to two Kronecker deltas. Then you have the next term. So we are going to rewrite everything here in terms of these operators. So what we have in the next one is that we have a delta 2, 3, a Kronecker delta, and that is going to leave us with just one contraction and two operators which need to be normal ordered. And you see now, if you look a little bit closer, so let's look at this term. So the Kronecker delta is given by the contraction here. And then I'm left with A1 and A4, which has to be normal ordered. And normal ordering gives me this minus sign. And then I have A4, A1. That gives automatically 0. So any term which does not include, as you can see here now, any term which does not include two contractions between two pairs of creation and annihilation operators is going to give us 0. So there you start seeing the power of Wick's theorem, that at the end, what we are going to need to evaluate are just contributions where all the operators are contracted. So by doing this example here, which is pretty straightforward, you can get a feeling of how you build up Wick's theorem. So you will have chains of such normal order products, so which is a rewrite of this. And I think to discover that, when Wick did it, that really helped a lot for quantum field theory and the development of quantum field theory. So this term, the second term, is going to be 0. And then we have a third term here, which actually is now two Kronecker deltas. So I'm going to rewrite this as an N, and then I have, say, the operators A1, A2, A3, A4. But now I'm connecting A1 with A3 and A2 with A4. Now, in order for these operators to construct a vacuum-to-vacuum expectation value, I need to interchange the order here. So I need to bring A1 close to A2. That means that I interchange A1 and A2, and that gives a minus sign. So this translates into, when you look at these contractions, if these lines cross, that corresponds to a minus sign. So you would typically say that here if you plot it like this, you would have two lines which cross. And that means that you have to interchange the order of the operators. And you see now that this gives us a minus sign, which is exactly what we had here, this expression. And now we can move on with all the other ones. So if we go to the second term, so the fourth term, sorry. This is A1, A2, A3, dagger, A4. And in that particular case, we have the contraction of A1 with A3. So we have this Kronecker delta, which you see here. So we have this. No, not that one. That was not the one I wanted to make. And in this case, we actually have this contraction. And that is also a normal order product where we have an annihilation and creation operator, and that gives automatically 0. And then we can continue in this fashion, and you will see that we have a final set of operators here where we have a set of operators where we now, the final one, which is just a normal order chain of operators, and that is also automatically 0. So if we now write this, continue and wrap it up, let me just write it down, the final expressions. So what we will have then is a plus, and then we have an n of A1, A2, of A3 and A4. And then we have the A2, A4, that's the next term. And then we have a plus, and then we have an n of A1, A2, and A3 and A4. And this final one is actually A1 to A4. And then the last term is the term with A1, A2, A3 dagger, A4, which we normal ordered so that the creation operators are to the left and the annihilation operators to the right. And that was the last term in the expression which you saw here, which is this expression here. And in that case, we had no contraction. And here, one thing to note before we take a small break is that all the terms like AI, AJ, dagger, this is automatically equal to 0, because that's the same as us calculating AI, AJ 0. So that is by definition 0. When we introduce this particle hole vacuum, we need to re-change the definition of the vacuum. And that will lead to that one not necessarily being equal to 0. And then we have, so this contraction here is 0. And then we have, due to the anti-commutation rules, that these are exactly equal to 0. So we don't list these in the number of contractions which we have. But you could now think of you running through all possible contractions. And that is Wick's theorem, which we will state after the break, and then we will prove it. So Wick's theorem, and that comes after the break, states, and I hope that these simple examples here can help in seeing how the theorem actually comes through and why it has this specific form. So just think of you now running through all possible contractions, and you sort everything in terms of no contractions at all, and just a normal order product, which is the last term. You have all the sums over one contraction, and then you have the sums over two contractions in this case. And it's only that one which survives when you have two creation and two annihilation operators. It's pretty easy to see here that if you have a different number of creation and annihilation operators, this is going to be equal to the same number of points which Norway collects when they qualify for the World Cup in soccer or the European Championship. 0. Sorry. I'm a soccer addicted, and it's always so disappointing when they don't collect more points than. Okay, guys. We'll take a small break and feel free to ask questions and everything. So before the break, we stopped at Wick's theorem states. So let's state Wick's theorem. And then we are going to run through some examples, and then we're going to prove the theorem. So Wick's theorem states the following. Let's write it down. So the theorem says that a chain of operators, and when we now are writing this chain of operators in the following way, what it actually means is the following. So we are looking at an expectation value but this is something you can generalize to any final and initial state. So we have a chain of operators where we are taking an expectation value, or it could be a transition probability, but let's just limit here ourselves to this kind of quantity. And we are going to write this in a sloppier way, where we simply write it like X, Y, Z, and W. So we omit this transition from a vacuum state to a vacuum state. So this is just a shorthand notation. So everything we do now, these operators, they always act on something, always. And this is what we discussed yesterday as well. If you're looking at commutation relations or anti-commutation relations, these are always the results of some operators acting on a specific state. So we can rewrite this now in terms of the normal order product of this chain of operators, X, Y, Z, W. That's the first term, and that is automatically 0. And if you go back to what we had before the break, if I can just change it. So before the break, you saw that we had this specific term here. No, this term, which was automatic, which gives us automatically 0. And this is after the contractions, it's a chain of operators which is normal ordered. So that means that when we perform these operations, there is always one contribution which corresponds to us having run through the anti-commutation rules, so that we have creation to the left and destruction to the right. And if you go back to this other example, you will see now that we have here as well for the free operator case, this is the same element. We run through all the anti-commutation rules which we could apply to the system, to this set of operators, and then we ended up with this term, which is the same as what you see here. And then for the case with just 2 operators, when we did that, we simply had this term which you see here, which then corresponds to this term here. So we've shown this for 2, 3, and 4 operators, and then we need to generalize it. And then the other thing which we noted was that for both the 3-particle case and also the 3 operator case, 2 operator case, and 4 operator case, we had a set of terms where we have one contraction. So since many of the cases with without the zeros are those which we end up listing, but we also have these cases which we never list because they are automatically 0. But what we can do then is simply to say that there is a sum here over, and this notation is a little bit strange, 1. So 1 means just one contraction. So only one pair of operator has been joined to calculate an expectation value. So it means that the rest of the operators are normal ordered. So I have X, Y, Z, the W, and this is a set where we have only one of these pairs of operators being contracted. So this is the sum over all terms with one contraction. And we see that immediately if we now go back to the expression which we had here. You see now that there is a term with one contraction here. That is also automatically 0, because when we normal ordered it, we are going to get 0. We have one contraction here. We also have a term with one contraction here, and we had a term with one contraction here. But then we didn't list those which are automatically 0. So we can then sum now over all terms with just one contraction. And that means if I now have a chain of such operators, then there has to be a set with 2 possible contractions. So I have this set of operators X, Y, Z to a W, and now we are contracting 2 of these, and I write it like this. So this is a sum over 2, over all pairs of contractions, pairs. So we have two sets of contractions with contractions. And this goes on up to we have reached n divided by 2, which is the number of operators divided by 2. That's the all possible set of contractions which we can make. If we have an odd number of operators, it's pretty easy to see that this has to be equal to 0. Because then there will always be a creation operator or an annihilation operator which doesn't match any of the other operators. And then we have a creation operator acting on vacuum and then going back to vacuum, so this has to be 0. And same with an annihilation operator. So this sum, or these terms, as we see here, they continue till, and let's just write the final term. So that runs over the sum, and I'm going to write this n. So n is number of operators, so number of creation and annihilation operators. And then I have now all possible operators are now being paired. So I have x, y, z up to w. And I write it like this. So this is contracted over all pairs of contractions. And you see that immediately if you go back to this case with 4 particles, not particles, but 4 operators, which we looked at previously, 2 creation and 2 annihilation operators. And there you saw that the only term which gave us something which was non-zero. So if you go back to this term, the only one for the case with 2 creation and 2 annihilation operators, which gave us something which was non-zero, is this term here and that term here. So the nice thing with the theorem is that it's only the last term which survives. So when I look at this expectation value, which I put up here in the beginning, this is equal. So what we have then is that this is equal to 0. And then simply the last term, the sum over all pairs of contractions of this normal order product of operators, x, y, z, like this. So that's the only term which survives, because all the previous ones will have a set of creation and annihilation operators. And when I then normal order it, there will always be some annihilation to the right, whatever we do. So if you go back to this simple case with 2 creation and 2 annihilation operators, you see now that a term like the one which you have here is always 0, because when we normal order it, it will be 0. And you see that in here, we have an A1. When that acts on vacuum, it gives 0. When these 2 guys act on vacuum, it will be 0. When this guy here acts, it will be 0. And the same with these states which you have here. So that means that all these kind of normal order product with less than all pairs of operators, which are creation and annihilation operators, are contracted, will not survive. So that means that when we are going to evaluate something, we just need to look at the last term in Wick's theorem. That's the only thing we need to look at. So let me try to convince you before we show the proof, the theorem, with an example which is relevant for the exercises also this week and next week. And the example which we're going to look at now is the calculation of a 2-body operator and the expectation value from a 2-body state to a final 2-body state. So we are going to take the same alpha 1, alpha 2 case, but now we're going to make life a little bit more complicated. So let's just use Wick's theorem on a case which would drive us crazy if we were to run this through the anti-commutation rules, like I did when we started. And then we go back to proving the theorem. So let's look at an example here, which we are going to see again and again. So the example, and as I mentioned, next week, I'm going to show you that you can rewrite the two-body operator in second quantization in a specific way. So I'm going to defer that to next week. But the two-body operator which we had, which we called for H of I for an interaction, which could be any kind of two-body operator. If you're doing, let's say, experiments on double beta decay, which is a hot topic for the standard model searchers, and searchers are breaking the standard model, then you would have a two-body operator. You can produce two neutrinos, or you can have a neutrinoless double beta decay. Just to mention some examples of two-body operators. What you would end up with is an operator which looks like this, and we are going to show that next week, alpha, beta, gamma, delta. And then we have the integral, which we often just call for a matrix element. There is an operator V, and then we have the states gamma, delta. And then there's something which confuses us in the beginning, which we will discuss more in detail next week, because due to the anti-symmetry for the fermionic system, the operators, they don't come in the order you would expect as you write the matrix element. So we have an alpha, A alpha, but then I have a destruction operator or annihilation operator for delta before gamma. This follows from the fact that we're dealing with fermions, and we will show that next week, how that comes through. But now we are just going to state it as it stands. And the thing we are interested in now is the calculation of the same states, but now with a two-body operator. And then we have an alpha 1, alpha 2 here. That's the same state which we looked at previously. And last week, no, not last week, but the week before, we calculated this by just setting up the Slater determinant, and we went through all the integrals. So we know what the answer is, and we would like to get the same answer back again. And let's see if we get the same answer. So in this particular case, what we would have then would be a factor of a half. I have this sum over alpha, beta, gamma, delta. And then I have my vacuum state. I have an A alpha 2, an A alpha 1. And then I have my A alpha, A beta. And these are creation operators. And I have my delta and my gamma. And then an A alpha 1 dagger. Now I need to go to the next line. So I have an A alpha 2 dagger acting on the vacuum state. And this is multiplied with this integral, which is something which we just tabulate. So one of the advantages of second quantization, the whole machinery assumes in a certain way that you can calculate these matrix elements or these integrals. You can either pre-calculate them and tabulate them. So that means that when you find the right alpha, beta, gamma, delta, you just look up a table. Alternatively, you have efficient ways to calculate these matrix elements on the fly. Or sometimes, if you're very, very lucky, if you're dealing with systems like the infinite electron gas, which is a hot system in condensed matter physics, the interaction is so simple that you can calculate the matrix elements on the fly. But often, these integrals are pretty complicated. And if you have 3 dimensions and 2 particles, these are 6-dimensional integrals. And many people have invested their research lives on methods to calculate these integrals in a fast and efficient way. I'm not joking, actually. There was a former master student here who did a PhD at the Quantum Chemistry Center, and the PhD was actually on calculating these type of integrals using what's normally called Gaussian orbitals with a Coulomb interaction. And you can calculate this in a very efficient way because since you want to have as many single particle states as possible, the table of these integrals becomes huge. And then at the end, you cannot store that table because you want a huge single particle basis. And then you need to have efficient ways to calculate these on the fly. But we are simply going to assume now, in all the exercises which we have, that these are either things we can tabulate or calculate easily on the fly. So the advantage of second quantization is something which you see here now, because we are never going to deal with the spatial degrees of freedom or the spin degrees of freedom, which are incorporated in the evaluation of this integral. So it's not only an integral, but it could also be an integral plus a sum over the spin degrees of freedom of the states which are involved. And then depending on the spin degrees of freedom, these matrix elements can be zero or not. And we will see that a little bit later. So for us now, the interesting thing is actually this. And that's a simplification in second quantization. We leave out specific degrees of freedom. But we have taken care of all the specific requirements on a fermionic system, like the anti-symmetry. So let's now look at this kind of ugly thing. And now we are going armed with Wick's theorem. We are waking up and we see the light. And hopefully this is a little bit easier. So we are going to rewrite this one. And now we are going to just we leave out the integrals. And I'm just going to show you the standard notation, which I will use often when I'm setting up these things. So this was a delta, a gamma, a alpha 1 dagger, a alpha 2. And what is pretty common is to skip the vacuum states, as we did previously here. So when we define this one here, we actually skip the vacuum states. So let's rewrite this and look at the contractions. So if we use Wick's theorem, there's only some few terms where we now have contracted all the operators. So I'm just going to write it like this, and now we are going to look at possible contractions. So a possible contraction which is non-zero is beta with that one, but that's something which is not interesting because that's just going to leave us with something which doesn't interact. And also, if you look at this one, this contraction is zero. So I'm not going to list that. I'm only going to list those contractions, possible contractions, which are non-zero. Because if I take a contraction like this one with, or suppose we take this one with that one, that will also be zero. Or a contraction with this one and that one will also be zero. So anything which goes from annihilation to annihilation, creation to creation, or creation operator to annihilation operator is going to be zero. So I'm not going to list them. So I only take those which are non-zero. So remember again that the way we have defined our vacuum, we don't need to include this type of contraction, which is zero by definition, and these type of contraction, which are zero by definition. So that simplifies the search for all the possible contractions which are non-zero. Okay? So these are just follows the definitions which we set up. So it means that the one which I put up here, this is something which will be zero. So we just take it away. Now what I can have is this one. That's a fully possible contraction. And here, I don't need to interchange operators because they are just together. So when I put in the completeness relation here on the left and the right side, I can immediately calculate this expectation mark, this contraction. And then I have this one. That's another possibility. And finally, I can take these two dudes here and put them here. Okay. So this is going to give me a integral when I take the Kronecker deltas now, because every contraction gives a Kronecker delta. That will give me a matrix element where the matrix element with alpha, beta, gamma, and delta, which we had, this is going to be equal to alpha 1. And that follows from this one. And then I'm going to have an alpha 2 here. I have my two-body matrix element. And then I get an alpha 1 and an alpha 2 here. Okay? So that's the Kronecker deltas which I get from the contractions, because what I get is the contractions are going to give me delta alpha 1 with a alpha, Kronecker delta with alpha 2 and beta, a Kronecker delta with gamma and alpha 1, and a Kronecker delta with a delta and alpha 2 here. And if you go back to the matrix element, which we started with, the generic one, where we now are running over all the possible single particle states the system can be in, this looks like this. That's the matrix element. By the contractions, I nailed down the quantum numbers because I have specified that my quantum numbers are given by alpha 1 and alpha 2 for the state which I'm starting with. That sound okay? So I'm just using Wick's theorem. And since the cases where I take, let's say, only 3 contractions are going to leave me with 2 operators, which have to be normal order, that will give me automatically 0. So Wick's theorem tells me now that I only need to look at these terms here. The next one which I can look at, which will be non-zero, is me taking the following. So let's just change page again. So let's just rewrite these operators, and then I'm going to write it in a little bit more compact form after this. So I have an A alpha, A beta, A delta, A gamma, A alpha 1, A alpha 2 here. So let me keep these 2 guys here. So these are just left like this. But now I let this A gamma go to alpha 2. So that means that I have to interchange the operators. So in order to get these contractions, I need now to interchange A delta with A gamma. And that gives rise to a minus sign, because you remember that the anti-commutation rules say that A delta, A gamma is equal to 0. So that means that A delta, A gamma is equal to minus A gamma, A delta. Okay, so when I do that, I get a minus sign. The other one stays as before. So this is going to give me a matrix element which goes like minus, and I have an alpha 1, alpha 2 of V, but now I have an alpha 2 of alpha 1. So in the previous case, what I did was simply to look at this term. Now I kept the left-hand side as it was, but let's now change it. So now I'm just going to write it like this. So we have a crossing here. So every time you cross these contraction lines, that gives rise to a minus sign. If I now still keep this one, so this is the new one. So this is number 2. This is a new set of possible contractions. And now I'm just listing those which can be non-zero. All the 0 ones are just left out. In this specific case, what we get now is a delta alpha 1 with a beta, and a delta alpha 2 with a alpha 1. And then I have a delta alpha 1 with a gamma, with delta, and delta alpha 2 with gamma. Since I have minus minus, that gives me plus. And now I have a matrix element which runs like plus, and then I have alpha 1, alpha 2, alpha 1 of V of alpha 2, alpha 1. But then we have assumed that these interactions are permutational invariant and translational invariant as well. So that means that if I interchange 1 and 2, I have the same matrix element or same integral. Remember, we discussed that in the beginning of the semester, that if we swap the 2 particles, due to the fact that the interaction depends only on the relative distance between the particles, then these matrix elements or integrals, they are independent of whether particle 1 is in a specific slot and particle 2 is in a specific slot. So this is the same as this alpha 1, alpha 2 of V, alpha 1, alpha 2. So you see now we are getting 1 here and 1 here with the same value. And then we have a factor of half. So when we're adding this up, we're just going to get 1. Then there's only one possible final element here. And that final contraction, there is a fourth contraction here. So which I'm just going to put up here. So the fourth one is going to give us the following. So we'll have the contraction alpha 2, A alpha 1, A alpha, A beta, A delta, A gamma. So if you look back at the previous case which we had now the case where we interchanged gamma and delta. Now we are going to keep this one as we did in the beginning, but we're now going to interchange these guys. That will give us a minus sign, and we will get a matrix element which now reads like alpha 2 of alpha 1 of V alpha 1 alpha 2. Now, if I now swap 1 and 2, I'm going to get the same integral. So this is the same as minus alpha 1 alpha 2 of V of alpha 2 alpha 1. So this is a symmetry which we imposed on the integrals. And actually people have searched for the breach of such symmetries experimentally, and they don't find any breaking of these specific symmetries down to what you might call the experimental uncertainty. There've also been very ingenious experiments to see if there are violations of the Pauli principle. And still, for most fermionic systems which have been studied, people haven't been able to see if there is a breach of the Pauli principle, down to experimental uncertainty, obviously. So if we then collect, so these are the only 4 terms which give us something which is non-zero. And clearly, if we had an exercise where you were using the anti-commutation rules and just go through this set of exercises, it's something we could have done in an hour, roughly. But you would have gotten lost in the woods of all the symbols, the subscripts, and it's so easy to interchange one of them. And then you have to trace back and where did I make the error and blah, blah, blah. So this is the way we will proceed with these kind of expectation values. And that means that when we now collect everything, the expectation value of alpha 1, alpha 2 for this specific operator, alpha 1, alpha 2, is now what we had before, is simply given by the integrals of alpha 1, alpha 2, minus, and then I have my alpha 2, alpha 1 of V, alpha 1, alpha 2. And the first term is what we call the direct term. And the second term is what we label as the exchange term. And that happens because we're dealing with fermions. So this is the anti-symmetry which is baked in the wave function. So we're getting back what we got when we use the standard so-called first quantization approach, where we calculated the integrals, we set up the Slater determinants, and then simply evaluated all the possible integrals. So everything is fine. Now, let's now move over to actually proving the theorem so that we can convince ourselves that this is something which applies to all chains of such operators. And that's not only limited to this case, which we set up as demonstrations with 2, 3, and 4 operators. So let's show Wick's theorem. So to show the theorem, we need a lemma. And this is probably where we will end today, so that we will have to continue with the proof of Wick's theorem next week. So today I'm just going to state this lemma. So if I have a chain of operators, so a chain of operators, and this chain of operators is given by X, Y, Z to W. And then we add a new operator. and we add this one to the right, a new operator. Which we just call omega. Then what we have is that the normal order product of x, y, z, which we had before. So just keep in mind that what we have showed is Wick's theorem for 2, 3, and 4 operators. So what we could think of now is that we have the theorem for, or we have this example for 4 operators, and we just add a new one. And we want to see whether the theorem holds. So we need this lemma. So what we want now to show is as if you take these 4 operators and you add a 5th operator. So this could be a creation or an annihilation operator, which we add to the 4 operators which we had previously. Now, what this lemma says is that we have n of x. This can be written as the normal order product of this quantity here, which automagically is 0. And then plus the sum over all 1 contractions, but which involve the operator omega only. So we have, so I'm writing this 1 with omega. It's a kind of a strange notation, but it means that only contributions between these operators, x, y, z to w, and then we have omega, where one of these operators connect with omega. So that means that all the operators we had, let's say in the 4 operator case, only one of them connects with the next operator we're adding if we have 5 operators. So we need this lemma here to prove the theorem. And this lemma is something which we can easily prove actually by the following observations. So let's write these observations down. So this lemma here, this is valid immediately if omega is an annihilation operator. Then you can easily see that that's actually the case. And we will discuss that a little bit next time as well. It is valid immediately. Immediately. If omega is an annihilation operator. By the way, let me do one thing so we don't hear these beeps while I'm, let me just. So this is the case because since then, if that's an annihilation operator, since then, if we take n of x, y, z to w, so this specific term, if you look at that one, that the first part is normal ordered. If I multiply that with a annihilation operator, it's already normal ordered. So this is pretty obvious, right? So this is already normal ordered. So 2, so what we will be left with then, and all possible contractions are 0. So because the type of contractions which we would have then would be something like this, and we know that is 0. And that's the same as an A times A. That is also 0. So if you go back here, you see now that if I do this, the first term is obviously normal ordered. And then the next term where I do the contractions has also to be 0 because it will involve only operations of this type here. And that gives us, with 1 contraction, that gives 0 anyway. So if it's an annihilation operator, it's pretty straightforward to see that lemma. And now what we have, if we now assumed, so we have assumed here, assumed, so let me just write all these things down. that the sequence is normal ordered. So that's the sequence of operators X, Y, Z, blah, blah. So that means ordered, yeah. So that's the sequence X, Y, Z up to W. And if it's not, you would simply have a rewrite, which just introduces a phase. So if the set of operators is not normal ordered already, you would just have a phase, and it wouldn't change the result here. So, so that would just introduce a phase in all terms of the lemma equations, which we have. The next part, which we need to think of, is that if this omega is a creation operator, the only thing which we need to prove then is that the XYZ operators, in case they are annihilation operators, that's the only case which can give us something different from zero. So if this omega is a creation operator, the thing we need to prove is that we need to prove the lemma if all X, Y, Z to W are annihilation operators. Since all types of contractions which we would have then, all A dagger contractions are equal to zero. So if the operators X, Y, Z are creation operators, then this is automatically zero, if omega is a creation operator. Because then the one contractions will automatically just be zero. So the what we need then is to anti-commute this omega through all the XYZ, and then you get the first term, which then will contain all the anti-commutators, which are then produced, they would give the second term. So let's now show this. So in this part 3, we anti-commute this this omega. We anti-commute omega, since it's now a creation operator, through all X, Y, Z to W operators. And if we anti-commute that one, we will then have something which will be normal ordered. So the anti-commutation of that operator is going to give us some Kronecker deltas, but we will have a chain of operators which then will give us, if they are annihilation operators, which then will give us zero. So that means that at the end, and then we will get, if we do that, we would get the first term in this expression, which we have here. So that means the term which you see here, this specific term, if we anti-commute it, you would get that specific term, get the first term, you would just get the first term in that case. And all the anti-commutators, which are then produced, give the second term. So all the anti-commutations which are produced, that gives the second term. Mutations, which are then produced, give the second term in that lemma theorem, in that lemma equation. give the second term, the term of the lemma. So I see my time is running out. So what we will do after we have stated this lemma, which we need to prove Wick's theorem, we will start next week from here. And we are going to look at some few examples of what this last statement 4 means. And then we're going to use this lemma to prove the theorem. And then we have the theorem. And this is the theorem which we will keep using when we are setting up all kinds of expectation values, transition probabilities, etc., etc. And it's going to give us a very compact way of representing quantum mechanical properties. And we're going to use that throughout when we look at different many-body theories. So this kind of second quantization language is a language where you now are replacing the spatial degrees of freedom. So when you look at Schrödinger's equation in what's normally called first quantization, you represent typically the system in terms of an infinity of interactions between the particles. When you now switch to second quantization, this kind of infinity of interactions which you would have when you represent a many-body system is then represented by an infinity of excitations, where you knock out a particle from a single particle state, you bring it to a higher state, and then you can bring it back again. So the kind of interactions you have in first quantization are replaced then by this way of thinking in terms of excitations, where excitations means you fill up to a certain level, the Fermi level, and then you can knock one particle out. They're interacting with some, let's say a laser, or they're interacting with each other, and then you can promote it to another configuration or another set of single particle states which are occupied. So the way we are going to rephrase the interpretation of a quantum mechanical system is in terms of these type of interactions. And for fermions, we are going to look at the excitations around the Fermi level. And that gives us a very compact way of analyzing a physical system. It takes some time to rephrase and rethink the way you interpret quantum mechanical systems. So just be patient. And sometimes I've actually had people who take this course and they say that it's only when I've studied quantum many-body theory and second quantization that I understand what you're saying, because it gives you a way to discuss physical systems which is intuitive. And you develop a kind of jargon where the kind of jargon refers to specific types of contributions to a system, whether that's an excited state, what that means in terms of excitations around the Fermi level, or whatever. So it gives you a very powerful tool to discuss what happens in a quantum mechanical system. And it also gives you a very powerful calculational tool. And you saw now that in this simple example of this teaser, where we looked at the two-body matrix elements, which we actually did spend some time in setting up for a Slater determinant for two particles. This is something which you can readily evaluate with Wick's theorem. Yeah?
You mentioned for my level, are we going to discuss temperature?
No, we will not have temperature, but the formalism can actually easily be extended to final temperature. So you could say that this course is a kind of, we've been having temperature before, but then we went into more Green's functional theory, where you can just make a rotation into complex time, and you can then interpret time as temperature. So that is, it's something which I haven't dared to do yet, because there's a lot of stuff we cover, but we could actually, if you guys are interested, we could discuss more time dependence and temperature dependence, if that's more interesting. Because we have some flexibility. The first many-body methods which we discuss are Hartree-Fock theory or mean field theories, which also link with density functional theory used in condensed matter physics. And then we have a method which is called full configuration interaction theory, which is actually you setting all the possible configurations. You set up the Hamiltonian matrix, and if you can diagonalize, you solve the problem. So these are basic methods which you will encounter in many applications. And then if we want to dive into temperature or time, then when we introduce perturbation theory, we could actually do that. If more people are interested in that, that can be done. So you have actually Wick's theorem for finite times, and that can be transferred to Wick's theorem for finite temperature as well. But it adds a level of complications. I mean, this is 10 credits, but we can always, I have to make sure that you guys survive. That's also an important aspect. Yeah.
Is this covered in any of the textbooks?
So in this textbook by Sabo and Oslund, you will find a lot of this stuff. So the first 3 chapters actually contain all this material. So I'm going to stop the recording, and then I will just upload the recording